Welcome to theastrodynamics.com and theastro.com. This website promotes the right way to build a commercial space catalog. The Astro has developed the analytic perturbed algorithms needed for rapid and automatic commercial space catalog building. This website is not funded or supported by or related to any government. The opinions expressed in this website are purely based on decades of research. I am Jim De. I develop computer codes for rapid and automated space catalog building. This website has many self-contained videos for catalog building. If you are familiar with differential correction, DC, you are ready to build an integrated IOD and DC algorithm for rapid and automatic catalog building. This video presents the overview of DC algorithms for rapid space catalog building. Again, if you are familiar with DC, you may skip to other videos of interest. This overview video of optical and radar DC provides preliminary understanding of 4 DC topics. 1. Input and minimum accuracies of optical and radar observations. 2. The Astro analytic optical and radar DC algorithms and their applicable operate regimes. Batch DC, BDC is for post-processing, and sequential DC by extended common filter EKF is for real-time processing. 3. Output of BDC state vector is at the first observation time, and the output of the EKF state vector is at the last observation time. However, the output of BDC or EKF state vector can be computed at any time if desired. 4. Key optical and radar equations in the analytic DC algorithms at the end of analytic BDC or EKF processing. If accuracy is desired, then the last iteration may include more perturbations with the use of numerical integration. For example, from LEO to GEO and ex-GEO to cislunar. Numerical integration should include higher order geopotentials, sun and moon perturbations. The Astro promotes commercial SP-type space catalog building with analytic IOD and DC algorithms to process observations collected by Earth or ECI ground-based sensors. For the two-body Gauss or Laplace optical IOD, only 3 observations are chosen from one track. For the two-body multi-web Lambert or radar IOD, only 2 observations are chosen from one track. One track of observations should contain reasonable number of observations and sufficiently long time span. With this prerequisites, IOD and DC may be successful. The purpose of orbit determination is to deduce the DC state vector at the first observation time t1 for batch DC as shown, or DC state vector at the last observation time tn for sequential DC by extended common filter, not shown in this picture. The 4 De Astro analytic DC algorithms 9 to 12 aim to process all observations in one track collected by Earth or ECI ground-based sensors. One track of observations should contain reasonable number of observations and sufficiently long time span. Source codes and real-world numerical examples of the 4 algorithms are provided in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. The key equations and how to solve for the final state vectors of the 4 algorithms are described in this overview video and the optical and radar DC videos in various details. The 4 De Astro analytic DC algorithms 9 to 12 highlighted in red are ECI based, and the ECI final state vectors are deduced from observations collected by Earth or ECI ground-based sensors. MCI in green and SCI in blue, DC algorithms are outside the scope of commercial space catalog building. Modifications of algorithms 9 to 12 from ground-based sensor site LLA to space-based sensor position vector is straightforward. However, due to the limited real-world observations collected by ECI space-based sensors, these ECI-based DC algorithms have been developed but have tested only with limited test cases. MCI in green and SCI in blue DC algorithms are outside the scope of commercial space catalog building. Commercial space catalog building concerns about objects in ECI or geocentric orbits, and at least 90% are in LEO in 2023. The astro, analytic, optical, and radar DC algorithms 9 to 12, which process observations from ECI ground-based sensors, aim to deduce ECI final state vectors as output of DC. These 4 ECI-based DC algorithms are not for MCI and SCI applications. Otherwise, DC state vectors will be erroneous or unreasonable. Note that highly eccentric cislunar trajectories, such as those of Artemis 1, of eccentricity greater than 0.9 between the Earth and the Moon, are geocentric and should be processed by the ECI-based DC algorithms 9 to 12. However, if the observations of an object collected from ECI ground-based sensors are in distant retrograde orbit, DRO, around the Moon, then MCI-based IOD and DC algorithms are needed. Also, in 1801, Gauss invented SCI-based IOD and DC algorithms to deduce the heliocentric orbit of the first asteroid Ceres from the observations of Biaggi. That is, applications of ECI, MCI, or SCI-based IOD and DC algorithms depends respectively on the object in geocentric, selenocentric, or heliocentric orbits. Accurate IOD starts with accurate observations. Accurate observations with field of view resolution of sub-arc second or greater than 5 digits beyond the decimal in degrees can be collected from 3 groups of optical and radar systems. 1. Expensive systems, from the $110 million Optical Space Surveillance Telescope, SST, to the over $1 billion Space Fence Radar. 2. Less expensive systems of the multi-million-dollar Geode and Starlink. 3. Commercial optical systems of $100,000 or less in 2023. The Astro, IOD, and DC algorithms have been able to deduce consistently accurate state vectors from commercial optical systems using real-world observations from LEO to GEO, ex-GEO to cislunar and beyond. However, expensive and less expensive systems are needed and useful for precision applications. In general, given reasonable optical observations time span, observations that are greater than 5 digits beyond the decimal in degrees are accurate enough for accurate IOD and DC algorithms. First, US Air Force B3 input format of optical observations. The decades-old US Air Force B3 format has restricted accuracy to 4 digits beyond the decimal in degrees. However, in year 2023, many inexpensive commercial $100,000 or less electro-optical EO systems can provide accurate optical observations of 5 or more digits beyond the decimal in degrees. In many IOD and DC test cases with shorter time spans, observations of 5-digit accuracy can produce more accurate IOD and DC state vectors. An important rule: the higher the observation accuracy, the shorter the observation arc or observation time span. That is, optical observations of 4-digit accuracy require longer time spans. In general, accurate optical IOD algorithms require at least optical observations of 4-digit accuracy with reasonable time spans. Second, propose free input format of optical observations. To improve optical IOD and DC accuracy, the proposed free format of optical observations that takes advantage of 5 digits or more accuracy is recommended. The ASTRO has built over 10 optical ECI-based IOD algorithms to process optical observations with different observation accuracies, short or long arc or time spans. Observations separated in seconds, minutes, or hours from LEO to GEO, ex-GEO to cislunar and beyond. Note that an optical observation file contains satellite ID, sensor ID, time, right ascension, and declination. Can you figure out the first observation of the US Air Force P3 input file? It is clear in the proposed free input format file. Radar observations are usually more accurate than optical observations, not to mention weatherproof, and therefore radar IOD and DC state vectors are usually more accurate than those of the optical. If accuracy is important and cost is no problem, radar observations are usually more desirable. A radar observation file contains satellite ID, sensor ID, time, range, azimuth, and elevation, and or range rate. Range is usually at least an order of magnitude more accurate than the angles. That is, if range area of radar observation is 10 meters, then azimuth and elevation errors are about 100 meters. The ASTRO analytic DC algorithms process radar observations to produce state vectors of circular, elliptic, parabolic, and hyperbolic orbits. Note that the proposed new free format takes advantage of observation accuracy with 5 or more digits beyond the decimal in kilometers and degrees. The Gauss or Laplace optical IOD algorithm requires 3 sets of accurate optical observations or 6 angle measurements alpha and beta to deduce the two-body state vector XIOD T2 at T2 and then propagate it back to T1, giving the IOD initial state vector XIOD T1 as input to a DC algorithm. In this picture, optical observations of the 2022 Artemis 1 between the Earth and the Moon are processed by BDC to output XDC T1. After a few iterations, the consecutive delta X T1 magnitude converges to a designated small value, say 1 meter, and then output the converged DC state vector XDC T1. That is, BDC deterministically solves for delta X T1 and XDC T1. The small blue funnel and the large red funnel show respectively how less accurate observations and accurate observations relate to DC convergence. Less accurate optical observations lead to more BDC failure and multiple state vectors. XDC T1. On the other hand, accurate optical observations lead to less BDC failure and almost the same state vector XDC T1. The ASTRO multi-web lambda IOD algorithm requires 2 sets of accurate radar observations or 6 measurements RAE to deduce the two-body state vector XIOD-T1 at T1 as input to a DC algorithm. In this picture, radar observations of the 2022 Artemis 1 between the Earth and the Moon are processed by BDC to output XDC-T1. After a few iterations, the consecutive delta XT1 magnitude converges to a designated small value, say 1 meter, and then output the converged DC state vector XDC-T1. Again, BDC deterministically solves for delta XT1 and XDC-T1. The small blue tunnel and the large red tunnel show respectively how less accurate observations and accurate observations relate to DC convergence. Less accurate radar observations lead to more BDC failure and multiple state vector XDC-T1. On the other hand, accurate radar observations lead to less BDC failure and almost the same state vector XDC-T1. To deduce a BDC optical or radar state vector or a DC orbit XDC-T1, the inputs are 1. The IOD initial state vector XIOD-T1. 2. Accurate sequential real observations of T1, T2 to Tn. 3. Ground sensor let long altitude LLA or space sensor position vector. The key equation is that of delta X T1, which contains the observation matrix H and the residual vector YTI minus Y hat TI, observed minus computed observation vector Y. H is a function of the analytic state transition matrix Phi and the analytic optical matrix O. Also, the computed observation Y hat TI is analytic, and therefore BDC becomes analytic because delta XT1 is analytic. Note that the observed observation vector YTI is given in the observation file. The output of BDC is the DC final state vector XDC-T1. After the first iteration on all observations from T1 to Tn, delta XT1 is computed, giving XDC-T1 equal to XIOD-T1 plus delta XT1. And the initial state vector is updated as XI-T1 equal to XDC-T1. Repeat to iterate on delta XT1 from T1 to Tn, giving the new XDC-T1 equal to XI-T1 plus delta XT1 and the new Xi equal to XDC-T1. Stop to iterate when BDC meets the relative and predicted IMS limits of convergence and the magnitude of delta XT1 satisfy the designated small limit, say 1 meter. Note that the final state covariance matrix H transpose H inverse may also be included as output of BDC if desired. To deduce the EKF optical and radar final state vector or a DC final orbit XDC-Tn, the 3 inputs are the same as in BDC. The computation of EKF contains 2 steps. 1. Propagation step. Before observation time Tk, propagation of error covariance matrix P minus Tk and state vector X minus Tk. 2. Update step. At observation time Tk, update of common gain, error covariance matrix, state vector observation matrix, residual observation vector, and delta X Tk. The key equation is that of delta x Tk, which contains the common gain and the residual vector y Tk minus y hat Tk. The output of EKF is the DC final state vector or the DC final orbit, x dc Tk at Tk equal to Tn. Starting with x dc T1 equal to x IOD T1 plus delta x T1 and process sequentially to n with x dc Tk equal to x plus Tk plus delta x Tk at Tk equal to Tn. Note that the final state covariance matrix P plus Tk may also be included as output of EKF if desired. For analytic optical BDC, algorithm 9, the key equation delta x T1 contains the observation matrix HTI and the residual observation vector YTI minus Y hat TI. Since the output state vector XT1 for optical BDC is at T1, the instantaneous observation matrix HTI equal to OTI times phi TI comma T1 is related to delta x T1 by the instantaneous state transition matrix phi Ti comma T1 for I equal to 1, 2 to n. However, for analytic optical EKF algorithm 10, the output state vector xtn for optical EKF is at Tn. Delta x Tk does not need the instantaneous state transition matrix phi to be related back to T1, and therefore HTK equal to OTK for K equal to 1, 2 to n. Fortunately, the analytic optical matrix OTI or OTK, which allows the analytic H to be computed, can be found in Herrick, Mansfield, or my book, Astrodynamic Algorithms for Rapid Space Catalog Building. Again, the residual observation vector YTI minus Y hat TI is analytic. Since the analytic and accurate observation matrix H can be computed in BDC and EKF, the numerical puzzles, or sometimes less accurate numerical observation matrix H, becomes redundant. The unsensed common filter UKF may be good for other applications, but not astrodynamics. For analytic radar BDC algorithm 11 and radar EKF algorithm 12, the key equations delta XTI and delta XTK contain the observation matrix H and the residual observation vector. The output state vectors for radar BDC and EKF are respectively at T1 and Tn. The optical matrix O is a 2x6 matrix for optical DC and expanded to a 4x6 matrix for radar DC. Again, further details of the analytic optical matrix OTI or OTK, which allows the analytic observation matrix X to be computed, can be found in Herrick, Mansfield, and my book. Since the analytic and accurate observation matrix H can be computed in BDC and EKF, the numerical puzzles, or sometimes less accurate numerical observation matrix H, becomes redundant. The unsensed common filters UKFs may be good for other applications, but not astrodynamics. In 1801, Gauss invented IOD and DC to process Piaggi's observations, and In 2022, DeAstro processed 10 optical tracks of Artemis 1 observations. These two examples show that for over 200 years, optical and radar IOD are deterministic. Any probabilistic IOD and DC are misleading. 4 stumbling blocks of coding DC algorithms. 1. Accurate real observations. Minimum requirements. 4 significant digits beyond the decimal in degrees and 5 significant digits preferred. 2. Normalized range and speed. For example, if geo range is 42,000 kilometers, normalized range is x approximately equals 6.6. The first term of the Gauss 8th degree polynomial equation, x to the power of 8, can be computed if range is normalized. 3. State vectors, partial derivative matrices, and state transition matrices must also be normalized if range is normalized. 4. IOD and DC coordinate systems. ECI-based IOD and DC algorithms can only be used for geocentric orbits and observations collected by Earth or ECI ground-based or space-based sensors. This video presents the overview of DC. The optical and radar DC videos present further details of how to compute the DC state vectors. Source codes and real-world numerical examples of the analytic optical and radar DC algorithms 9 to 12 are included in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. An accurate space catalog is the mother of all space operations. Today, in 2023, many commercial space companies are building their own commercial SP space catalogs. However, if they are using HEV4 for analytic orbit propagation, they have to build their second TLE space catalogs. Also, they have to overcome 3 challenges of commercial space catalog building that DeAstro already accomplished. 1. DeAstro proprietary Windy-based analytic astrodynamic algorithms used directly the accurate SV data for automatic processing of millions of radar and optical observations per day. 2. Century-old insight to pick the correct range when optical IOD suggests 3 possible ranges, otherwise DC will be complicated. 3. Centuries-old insight to pick the correct Lambert solution when radar IOD suggests 2n plus 1 possible Lambert solutions, where n is the number of orbit revolutions. Otherwise, DC will be difficult. The professional version of DeAstro astrodynamic algorithms include the solutions to the 3 challenges. Commercial space catalog is the key or heart of commercial space businesses that are growing rapidly from hundreds of billions to trillions of dollars per year. I am Jim De. Thank you for watching this video of DeAstro.com.